penuh kesungguhan. Akademi YouTuber Malaysia langkah laksana dengan jitu, penuh bermisi guru AYU mencapai misi yang satu, bermisi kita bantu.
Tahniah. Siaran langsung ini dibawakan khas kepada anda oleh Akademi YouTuber Malaysia. Tumpukan perhatian anda. Siaran langsung akan bermula sebentar lagi. Link sijil akan diberikan di hujung siaran ini. Pastikan diisi dalam tempoh yang ditetapkan. Terima kasih.
Assalamualaikum warahmatullahi wabarakatuh, and good evening teachers, parents and all the wonderful students. Welcome to Pusat Tuisyen Academy YouTuber bermula percuma, selamanya percuma. How are you doing today? Hope all of you are ready for today's lesson. Before we proceed, let's begin our session by reciting Umul Kitab for Muslim. For the non-Muslim, may pray according to your own religion. Al-Fatiha. Alhamdulillah. Let me introduce myself. My name is Shahnon from College Matrikulasi Pulau Pinang, and my teaching experience 22 years, and my position is Ketua Panitia Kimia Prayu, and my channel is Shahnon channel. Okay, and this is my team Kimia Prayu. We have a teacher Kong, Cikgu Bawa, me and teacher Tangs, and this is mathematics Prayu led by teacher Im. Biology Prayu led by Cikgu Faiza, and Perakaunan and Economy Prayu led by Madam Fizi, and last but not least, Physics Prayu led by Madam Rosmaya. Alright. And this is Academy YouTuber Malaysia portal. Alright. We can get more information from this portal. And this is aplikasi Academy YouTuber, aplikasi koleksi video pendidikan terbesar di Malaysia. You can download it from Google Play, right? And install it in your handphone. Alright. Without much ado, let's go to our lesson today. Our lesson today is chapter 2. Chapter 2 in matriculation syllabus. It will cover atomic structure, 2.1 Bohr atomic model, 2.2 quantum mechanics, and 2.3 electronic configuration. Alright. First of all, we look at Bohr atomic model proposed by Niels Bohr in 1913, right? And it has the atom. This is theory of Bohr atomic model. We have atom as a center, and around it we have a nucleus, right? And around it we have an electron. Okay, and here is 4 Bohr's postulate. Number 1, electron move in circular orbit around the nucleus. Alright. Number 2, in the permitted orbits, the energy associated with electron motion is quantized or fixed value. Number 3, energy is emitted or absorbed by an electron when it transits from one energy level to another. And the fourth one is no energy is absorbed or released when the electron is circulating in an orbit. Alright, from this second Bohr postulate, actually we can has this formula. Okay, the energy of an electron in its level is given by En equal to negative RH 1 over n squared. RH is variable constant, 2.18 exponent negative 18 joule, and n is identified the orbit of electron, positive energy, 1, 2, 3, and so on. Alright. And energy is 0 if electron is located infinitely far from nucleus and equal to infinity. Okay, this from second Bohr postulate. For the third Bohr postulate, energy is emitted or dissolved by electron when it transits from energy level to to another. We can has this formula actually, but before this, we look at the term in Bohr atomic model. Ground state. What is ground state? The state in which the electron have their lowest energy. For hydrogen, the lowest energy for hydrogen is n equal to 1. Okay. Excited state, the state that has higher energy than the ground state. Okay, higher than ground state, that means n equal to 2, n equal to 3, n equal to 4, and so on. And energy level. What is energy level? Energy associated with a specific orbit or state. We call it energy level. And also we have definition of line spectrum. What is line spectrum? A spectrum that contains discrete line. In each line correspond to specific wavelength and frequency. In atomic spectrum, we will have this kind of spectrum line. And this one we call it line. As we can see here, we have a red line, yellow, green, blue, and so on. This line produced by excited atom and ion as the electron fall back to lower energy level. As we mentioned here, we have a ground state, excited state. Right? So from excited state, higher than lower energy level, it fall back to lower energy level. Then it will the radiation emitted will give a specific wavelength and frequency, right? So this means each line here, we have a 1, 2, 3, 4, 5 line here, correspond to a specific wavelength or frequency. Okay. So this is how we calculate the energy change during electron transition, how we want to calculate the energy, the frequency, the wavelength, and so on. And as I mentioned before, here we have 4 formula, and these 4 formula come from the third Bohr postulate, right? The third Bohr postulate, this one. Energy is emitted or absorbed. All right. Number 1 is delta E equal to H nu. Okay, delta E is the difference in energy. H is a Planck constant. Nu is a frequency. Number 2 is delta E equal to H over lambda. Okay, H is Planck constant. C is speed of light. Lambda is wavelength. Okay, H over lambda. And the third formula is delta E equal to RH 1 over n I squared minus n f squared. And we will use the Rebut constant is 2.18 exponent negative 18 joule. And the fourth formula is 1 over lambda equal to RH 1 over n1 squared minus n2 squared. And n1 must be less than n2. And we will use the value of RH 1.097 exponent 7 per meter. Okay, how the formation of line spectrum of hydrogen atom. Okay, this is what we call energy diagram. Okay, energy diagram. First of all, the electron at ground state here. Okay, when it's absorbed energy, electron at ground state will excite to higher energy level. Some of them will excite, let's say, to n equal to 3. Some of them will excite to n equal to 4. And n equal to 5, and so on. Alright. When it's excited to higher energy level, the electron actually stay unstable. Okay? At excited state here, actually is unstable. It will fall back to lower energy level. Okay, when the electron fall back to lower energy level, the radiant energy are emitted in the form of light, and then with a specific wavelength and frequency. Okay, this is what happened. And the best thing about when it's fall back, we have actually a series of a spectrum. Okay, when the electron fall back to n equal to 1, then we will have what we call Lyman series. Okay, for example, here we have electron at n equal to 2 fall to n equal to 1, or 3 n equal to 3 to n equal to 1. This will form like a series. And if the electron fall to n equal to 2, then we will have a Balmer series. And then Pustian series, when electron for higher energy level to n equal to 3, Pustian series. Bracket, when electron at higher energy level fall to n equal to 3, okay, and P-funk series when at higher energy level to n equal to 5, right? Okay, we have a 5 series of in hydrogen atoms in the syllabus of multiplication. All right, we look at this example. Okay, now we have a Pustian series of line spectrum of Pustian series. Okay, A, B, C, D, E, and which the question is which of the line in the Pustian series correspond to the longest, all right, longest wavelength of photon. Okay, the longest wavelength. Okay, we have to understand that the line A here is in Pustian series. If you look at here, this is Pustian series. The electron will fall back to n equal to 3, right? N equal to 3. Okay, make it side by side. All right. This is first line in Balmer's in Pustian series. That means electron fall from n equal to 4 to n equal to 3. This is for first line in Pustian series. This is second line. Okay, this is second line. This one. Electron fall from 5 to 3. This one 6 to 3, 7 to 3, and 8 to 3. Okay. Okay. Look at here. This is energy, right? This is energy. This is energy for first line in Pustian series. And here is the energy, the ratio of energy of second line. We can see here the first line has a lower energy compared to a third, the second line, and for the third line in Pustian series. So we'll use this formula. All right. The delta E here, the energy inversely proportional to the lambda or wavelength. The higher the energy, the shorter the wavelength. All right. So if you refer to this question, the longest wavelength should be the lowest in the lowest in energy. It should be line A. Okay, line A has the lower energy compared to B, C, and D, and that means it has the longest wavelength. Okay, and question number 2 state the transition that gives rise to the line E. Line E here 8 to 3. Okay, as I put it here, this is 4 to 3, 5 to 3, 6 to 3. So the electron move or transit from n equal to 4, n equal to 8 to n equal to 3. All right. Okay, we look at this example, the second example here. Calculate the energy that is associated with the Balmer series of the hydrogen atom. Okay, the Balmer, we already know that the final and it will fall to n equal to 2. And for the second line, 3 to 2 is first line, 4 to 2 is the second line. We will use n equal to ni is 4, and then we use formula this delta E equal to RH 1 over, because we have the n here, okay, n. So RH is 2.18. Remember RH for energy we will use 2.18 exponent negative 18, and 1 over 4 squared, 2 squared, and use your calculator, and the answer is negative 4.09 exponent negative 19. Negative here indicate that energy is released when electron fall from higher energy level to lower energy level. Alright. The second question is wavelength. Okay, wavelength. So you can use this formula: 1 over lambda equal to RH 1 over n 1 squared minus 1 n 2 squared, and n1 must be less than n2. So because this is lambda, you cannot use 2.18 exponent negative 18 joule. We have to use 1.097 exponent 7. And remember, this one must be less than n2. All right. And then after we get the answer in meter, change it to nanometer times exponent 9. So 486 nanometer. Okay. And see the frequency. Okay. So we just use this formula, nu equal to c over lambda. C is speed of light, 3 exponent 8 molar per second. And lambda, we have to use in meter, 4.86 exponent negative 7 meter. And the answer is 6.17 exponent 40 per second or hertz. Okay, frequency we can use per second or hertz. All right, and the second one that's very important in bioatomic model is to calculate the um, ionization energy. Before that, what is ionization energy? Minimum energy required to remove 1 mole of electron from 1 mole of gases ionized at ground state. That means Ni should be n equal to 1 and the final should be infinity. Okay, infinity. Look at this diagram from n equal to 1 ground state until infinity. Alright. So we use delta E. Delta E is RH 1 over n I squared minus n squared. Okay. And then the answer is 2.18 exponent negative 18 joule. This is the minimum energy required to remove 1 electron in 1 atom. Okay. To make it in 1 mole, okay, we need 1 mole here. We have to multiply with Avogadro constant. Okay, 6.2 exponent 23. The answer is this one. And change it to kilojoule divided by 1000. And the answer is 1312 kilojoule per mole. Okay, this is minimum energy required to remove 1 mole of electron from 1 mole of gases and atom. And if we refer to the line spectrum here, okay, this is Lyman series. Of course, we have to refer to Lyman series because the electron at n equal to 1. It's referred to the continuum limit here. Okay, we cannot refer to the first line because first line here is electron from n equal to 1 to n equal to 2. We cannot refer to the n second line because second line is from 1 to 3. But for continuum limit, 1 to infinity, yes, this is we refer to this line that is what we call it at continuum limit to refer to the ionization energy of hydrogen atom. Okay, 2.2 quantum mechanics. Quantum mechanics. If you look at the Schrödinger wave equation, wave mechanics is a mathematical model which can be used to define probability of finding electron, and it solves the equation using wave function, the probability of finding electron, the shape of the orbital, and so on. If we focus here, where is it? Okay, if you focus here, okay, we can see the different shape of probability of finding of electron here. Okay, look like spherical here, but here look like dumbbell here. Right? And okay, oops. And here we have the terms, what we call atomic orbital. What is atomic orbital? Three-dimensional space around the nucleus whereby the probability of finding electron is the highest. Three-dimensional space, probability of finding electron. Here we there is no term of orbit. Orbit only in Bohr model. In quantum mechanics, the terms that we use is orbital. All right. We see the different orbit and orbital. All right. And each electron in an atom is characterized by 4 quantum numbers: principal quantum number, azimuthal quantum number, magnetic quantum number, and spin quantum number. We'll go through with these 4 quantum numbers. Number 1 is principal quantum number, n. What is principal quantum number n? Indicate the relative size of an orbital, describe the relative energy level of shell, describe the distance of electron from atomic nucleus, and n is a positive integer, 1, 2, 3, and so on. The larger the n, the greater the energy level, and the farther it's from nucleus. Okay, shell n. Okay, we have n equal to 1, 2, 3, and so on. This is the orbital size. We can see that the orbital size increasing from n equal to 1 to n equal to 4, and also the energy increasing from n equal to 1 to n equal to 4. Okay. The second one is azimuthal angular momentum for the number. We use L as a symbol. Okay. Indicate what? Indicate the shape of orbital. Describe the relative energy of subshell. We call it also as a subshell for azimuthal quantum number. For principal quantum number, we call it as a shell. Okay. And the value of L depend on principal quantum number n. Value of L are from 0 to n minus 1. For example, for n equal to 2, the value of L only 0 and 1, cannot more than 2. Okay, this is 2. The value, the number is 2. For L is 0 and 2 only. For n equal to 4, only 0, 1, 2, 3. Okay, not 4, only 0, 2, 3. Okay, and L is generally designated by the letter SPDF. For L equal to 0, we'll use symbol S like this, and this is orbital shape, spherical. For L, we use P. For L equal to 2, we use D, and with a different shape of orbital. For S is spherical, P is dumbbell, T is cloverleaf. Alright. Now, we go to magnetic quantum number. Indicate orientation of orbital in space around the nucleus. Describe the number of orbital in one subshell, and possible value of M depend on the value of L. Okay, let's say we have L equal to 0, M only be 0, because negative 0 is 0, positive 0 is 0. That means it only has one orbital in S subshell. For L equal to 1, M could be negative 1, 0, and positive 1. So 3 orbital. For L equal to 2, M can be negative 2, negative 1, 0, positive 1, and positive 2, 5 orbital. Right? And the last one is electron spin quantum number. Define the spinning motion of electron on its own axis. 2 possible direction, clockwise and anti-clockwise. Alright, for example, positive half, okay, we will use positive half and negative half for spinning motion of electron. Alright, now we want to combine all the 4 quantum numbers and see the relationship between them. Okay, n is principal quantum number, or we call it shell. For L equal to 1, L equal to 0, no problem about that. Okay, 0 is less than number 1. And 0, the subshell designation is 1s. And for M, also 0. And the spin quantum number is positive half and negative half. And number of orbital in subshell is 1. Okay, 1. 1 refer to 1s. Okay, only 1. And maximum number of electron is 2 lah, because the maximum number of orbital in orbital only 2. Okay, one is clockwise and one is anti-clockwise. Okay, look at this shell 2. Shell 2 has 2 subshells, 0 and 1. For 0 is 2s and 2p for L equal to 1. And M for 2s is 0 and negative 1, 0 and positive 1 for 2p orbital. Alright, here we have one orbital in 2s subshell and 3 orbital for 2p subshell. And the maximum electron, of course, 8, because 4 times 2 is 8. and so on. What happened to the shell 3? Okay, and here is the shape of atomic orbital. For s orbital, spherical shape with nucleus at the center, and the probability of finding electron at the distance r from nucleus is same from all direction. Okay, when L equal to 0. Okay, this is shape of orbital for 1s, for example. This is 2s, and this is 1s, for example. This is 2s, and this is 3s. Okay, we can see the difference in size. And for p orbital, when n equal to 2, we have -1, 0, and +1. All right, maybe this one is m equal to -1. This is 0, 0 in +1. Okay, maybe we don't know. As we can see that it has the shape is dumbbell, and px, py, pz different in orientation, oriented to x-axis, oriented to the y-axis and the z-axis. Okay, you can see different, same energy, same size, but different in orientation. And for D, we have 5 orbital here, -2, -1, 0, +1. Maybe this one is a -2, this one -1, this one 0, +1, and +2. Okay, something like that. And we have 5 d orbital, dxy, dxz, dyz, dx minus y squared, and dz squared. And how to sketch this orbital, I will give the link in description. Okay, because it will take a long time to sketch this orbital. Okay, we look at the example here. How many orbital are there in 3D subshell? Okay, 3D subshell, look at here. 3D subshell. Okay, this is 3D subshell. 3D subshell. It has 1, 2, 3, 4, 5. 4, so 5 orbital. Alright, this is the answer. 5. Okay, 5 orbital. What is the maximum number of orbitals that exist in shell n equal to 3? Shell n equal to 3. Okay, back this one. This is shell 3. This is shell 3. Shell 3 has 3 subshell, 0, 1, and 2. Subshell 0, subshell 3s, that means 3s, 3p, and 3. 3s has 1 orbital, 3p, 3 orbital, 3d, 5 orbital. So total is 9. Okay, 9 orbital. Okay, this 9 orbital. And which of the following orbital are allowed? This one we have to refer to 2.3 after this. Okay. Number 4. Which of the following quantum number are not allowed? Explain your answer. Okay. Make it bigger. For this one is for n, principal quantum number. This is azimuthal quantum number, magnetic quantum number, and s, spin quantum number. For n equal to 2, L equal to 1, this is allowed because less than 2. M equal to +1, this is allowed because M depends to L, +1, and S, of course, +half. So this is allowed. For B, 3, yes, this is allowed. 0 also allowed because 0 is less than 3. 0 for magnetic quantum number also allowed because -0, 0, and +0, and -half. Alright, this is allowed. Not allowed is this one because 4 is same with 4. This is not allowed. When n equal to 4, L can only be 0, 1, 2, and 3 only. Alright, this answer for this question. And now we go to electronic configuration 2.3. Okay, 2.3 electronic configuration. What is electronic configuration? Electronic configuration of an atom ion, it describes the arrangement or distribution of electron in atom. We can denote the electronic configuration by using orbital diagram. This is orbital diagram. Okay, this is orbital diagram. We have a box here. Sometimes we can use platform, and this is SPDF notation. Okay, 1, S2, and so on. Each orbital is represented by a box, and each electron by arrow. We have a box arrow. Up arrow represent electron with a positive spin, positive half, and down arrow negative half. Okay. To fill electron um, in an element, we have to use three principle and rules. Okay, we have Ahbau principle, Pauli exclusion principle, and Hans rule. Okay, we go one by one. Number one, we call it Ahbau principle. State that electron occupy atomic orbital of lower energy first before they fill orbital of higher energy. Okay, higher energy. And this is how we fill 1s, 2s, 3s, and so on. Okay, look at here, 1s, and then we have 2s, 2p. Okay, and then we have 3p. Okay, here, 4s, p. Okay, this is how Ahbau principle, 1s, 2s, 2p, 3s. But for 3s, 3p, and 3d, why 4s is here? Because we follow Ahbau principle. Okay, we just draw this diagram and then follow this instruction. 1s first, and then 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, and so on. Okay, this is how Ahbau principles all about. And Pauli exclusion principle, no two electrons in an atom can have the same 4 quantum numbers. Any orbital can hold a maximum of 2 electrons. In other words, this is the right one for Pauli exclusion principle. In one orbital, only 2 electrons with different spin. Okay, this is cannot because same spin. This cannot because 3 electron. Okay, cannot. All right. And then Hans rule. What is Hans rule? State that when electrons are added to the orbital of equivalent energy or general orbital, each orbital is filled singly with electrons of the same spin first before it's paired. What does it mean? Okay, equivalent energy refer to p orbital and d orbital because this is p orbital. Okay, 2px, 2py, and 2pz example. As we know that in one electron, one orbital, only 2 electrons. This one is wrong because filled singly with electron of the same spin. This one is a double electron in one orbital, cannot, according to Hans rule. This one singly, okay, but different spin, also cannot, according to Hans rule. This one okay because singly with same spin before it pair up. Okay, this one okay. For example, we have okay, I make it like this. Oops. Okay, let's say we have 8 electron. This one is 1s, 2s, and this one is 2p, right? We have 8 electrons. How to fill according to Hans rule? Okay, Ahbau and Pauli exclusion principle. Okay, I have 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. All right, that's how we fill electron according to Ahbau, Pauli exclusion principle, and Hans rule. Okay, example. Draw orbital diagram of the electronic configuration of aluminium. Proton number is 13. Also write the ground state of electronic configuration for aluminium and Al3 plus ion. Okay, let me redraw. Okay, like this. This is 1s, 2s, 2p, 3s, and then this one is 3p. Okay, how many? 13. Okay, 13 electron. 13. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11, 10, 11, 12, 13. That. Or in SPDF, okay, 1s here has 2 electrons, so 1s2, 2s here also 2 electrons, 2s2, 2p here has 6 electrons, 2p6, 3s here, 3s2, 3p1. That's how we change from orbital diagram to SPDF notation. And for Al3 plus, we have to remove electron from outermost. We call it outermost shell. So this is 1 electron here, and another 2 electron here. You just remove it. So it's become 1s2, 2s2, 2pc. Okay. Okay. Draw orbital diagram. Electron configuration of oxygen. Also write the ground state. Okay. So this is orbital diagram of oxygen. 1s2, 2s2, 2p4. Okay, like this. Okay, and this is SPDF notation. And then for O2 minus, we have to add electron. That's mean I will add electron here. Okay, here 1 and here. So it's become 2p6. Okay, this is orbital diagram. I will add 2 electron. Okay, for transition metal, titanium 22. This one, first we have to follow Ahbau principle. Okay, Ahbau principle. 1s2, 2s2, 2p6, 3s2, 3p6, 4s first before 3d. Okay, even though 4s is higher energy level compared to 3d. Okay, 4 for shell 4. Okay, 4s at shell 4, 3d at shell 3, but we have to fill 4s first according to Ahbau, right? So titanium is 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2 here, and then 3d2. But when we usually we will change it, we will make it like this: 1s. Okay, this is shell 1, 2s2, 2p6, shell 2, 2s2, 2p6, 3d2, shell 3. Okay, we will group them. We will combine them. We will gather them in a subshell in a shell. Okay, 3s, 2, 3p6, and 3d2. Okay, like this. And then question is 2 Ti2 plus. That means we have to remove. To remove it, we have to remove 4s. 4s at outermost shell. Okay, 4s. So it's become 1s2, 2s2, 2p6, 3s2, 3p6, 3d2. Okay, if you maybe if you still at this form, you will remove 3d. Okay, that's not right. Okay, and this one is anomalous case. Okay, we call it anomalous case in filling of electron that does not follow Ahbau. Okay, for chromium, for example, the proton number is 24, and the electron of course 24 for chromium atom. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. This is what we expected configuration according to above. Okay, 4s2, 3d4. But what happened in actual configuration? 4s1, 3d5. This is the actual configuration of chromium. Okay, why? This is the reason given by the scientists. Extra stability is gained by having half-filled 3d orbital. This one we call it half-filled 3d orbital. This one we call it partially filled. This one partially filled. This one half-filled, right? This one is partially filled. Half-filled 3d orbital has extra stability. And energy of 4s and 3d orbital are very close. Actually, 4s and 3d are very close, causing one of the electron in 4s jump to the 3d orbital. Okay, jump to the orbital. This is the reason given by the scientists why the actual configuration of chromium is like this. Not 4s2, 3d4, but 4s1, 3d5. Okay. And the same goes to copper here. Proton number is 39. Okay, this is expected 4s2, 3d9. But the actual configuration for copper 4s1, 3d10. And this is the reason given by the scientists. The atom with the completely filled, this one we call it completely filled, okay, completely filled, 3d subshell has spatial stability compared to this one only partially filled. Remember, this is partially filled. We only has fully filled or completely filled, partially filled, and partially filled, completely filled, only that one, and half filled, right? And the difference in energy between 4s orbitals is not significant. There's the one of the pad, one of the here 4s is given to the 3D, and the actual configuration of copper like this 4s1, 3d10. Okay. Okay, I hope you can understand topic 2.2 very well after this. So we will see in another session. And Assalamualaikum warahmatullahi wabarakatuh and goodbye. Bye bye.